So now we're going to jump into chapter 8, where we're going to take a lot of the things that we learned about the atomic structure and start applying it to bonding, right? So when atoms are held together, how are they held together? And chapter 8, we're going to really look at it in terms of, as you can see from the title, general concepts. So types of bonding, how those elements are held together. We'll look at some things called bond energies, basically how much energy does it take to break a bond. All kinds of things like that in this chapter. In chapter 9, we're going to look at bonding from a more orbital-based standpoint. But there are going to be some things we need to have just as some basics in here as we start to talk about bonding. And a lot of it's going to come down to the energies involved in bonding. Okay. So the first thing to think about as we start down this path is, well, let's just think about ionic bonding in general. So we're going to talk about ionic and covalent. We're going to start out just from a very simple standpoint with ionic bonding and then covalent bonding, and we're going to come back more in depth with this. But we know that there are two types of chemical bonds. One of those two types is ionic bonds, okay? Now, ionic bonds are, and I tend to not think about them as bonds so much as attractive forces, because of the nature of what bonding sort of for me means, based on some of my training as an inorganic chemist. But basically, the reason that I think of ionic bonds as not really being bonds so much as attractive forces is because we're talking about just two charges that are pulled in towards each other, okay? And there's an energy of attraction associated with a positive charge being pulled in and attracted to a negative charge, okay? Now we're going to explore this a little bit more later on as well, but there's some basics to this that we need to understand. So the energy of attraction between two ions. So here, this figure here that I'm circling, right, that's a sodium chloride crystal, or at least shows a space-filling model of the sodium and chloride ions in this particular atomic ionic compound. And so those atoms are held together by having opposite charges, and the strength of that attraction is related to the magnitude of the charges, which in this equation here, right, this is governing, this is Coulomb's law, which basically tells you the energy of attraction between two ions. And so you have two things in terms of charges. Those are Q1 and Q2. Those are the charges of the ions, so +1 and -1, which says that the energy of attraction that is minus in the negative range, right, says that they go to a lower energy. If there's a plus charge and a minus charge, they're attracted to each other, which means if you compare two charges that are the same, or really more so, two charges that aren't interacting with each other at all, positive and negative charge are attractive to each other, so the energy would be lower. It would be more stable when these two ions of opposite charges interact. Okay, and that's compared to, say, a zero interaction of non-charged substances, okay? So the charges matter. If they're the same charge, they're going to repel. And we know that based on what we've talked about as far as charges and interaction of charges in the past. But it's also not just, so it's not just the charges that are important, right? It's also the distance between those charges, because we sort of frame this a lot of time with, as far as magnets and charges, right? Because of it's things that we have interacted with in our lives. And we know that as two magnets are put closer and closer together, right, they're more likely to snap together because the force or the energy between those magnets increases as they get closer together, similar to how charges work. And so the distance between the two charges is also going to be very important for understanding the energy of the attraction between those ions, okay? Something we're going to look at as far as the distance between those particles is basically the sum of what's called the ionic radius of the two ions. So sodium and chloride are going to have basically, if you consider them to be two spherical ions, right, you can look at the ionic radius of sodium compared to the ionic radius of chloride, and the ionic radius of chloride, and that's the distance between the two nuclei of neighboring ions. And so that's going to be what we consider a bond length, or the D, okay? And so that distance is going to be what helps us to understand the forces between those two ions. So as those ions get larger, the forces are going to be smaller. As those ions are more charged, or as you go from a +1 to, say, a +2, that's going to cause an increase in the energy of attraction. And we're going to look at that more in depth as we start to look at the size of ions in a little bit. And so that's ionic bonds, just kind of a quick introduction to them. We'll do more on that in a bit. The other type of bond that we've talked about, is covalent bonds. And so when we consider covalent bonds, there are a couple of things that are really important, okay? In order for you to have a covalent bond, one of the things we have talked about in the past is that you have to have atoms that share a pair of electrons, okay? That's the thing we've talked about in the past, right? When you have a covalent bond, you have two atoms. So in this example, you have a hydrogen atom and another hydrogen atom that will come together to form an H2 molecule. And when we've drawn out a Lewis structure for this in the past, right, it looked something, well, we haven't drawn out, I guess we're about to get to Lewis structures, excuse me, I'm getting ahead of myself. So we're going to get, but when we've drawn structures of this in the past, we've used the line in between the two to represent a covalent bond. And so that covalent bond is representing a shared pair of electrons, okay? If I look at the two atoms coming together, that shared pair of electrons is right between those two atoms. Both of those nuclei are pulling on those electrons and they're sharing them. That's what we've talked about as far as covalent bonds in the past. Something we haven't gone into is how the orbitals come into play. And so in order for you to have a bond, you have to share the electrons. But where you're going to find those electrons is you're going to find those electrons in orbitals that overlap. And so if you consider a hydrogen atom, each of these hydrogen atoms, as they're written here in their ground state, well, each of these places where you find the electron is going to be a 1s orbital, right? And so when you have a bond between two hydrogen atoms, those two 1s orbitals, the 1s orbital from each of those hydrogen atoms has to overlap. And in the region where you have this overlap, right in here, right, that's where you tend to see those electrons being shared. And that's something we call a localized bonding model. And we're going to spend more time on that a little bit later. But those are the two things, right? You need to have orbitals that overlap from each of the bonded atoms, and they have to share a pair of electrons, okay? Now, when it comes to describing covalent and ionic bonds, one of the things that we tend to look at is called the bond energy. Now, we call it bond energy for covalent bonds. We sometimes loosely call it bond energy for ionic bonds, whereas it should be called the lattice energy. Basically, the bond energy is the energy required to break a bond, okay? And that's a pretty important thing, right? The energy required to break a bond or pull two atoms apart, okay? So the energy required to pull two atoms or ions apart. And if we're talking about ions, we should really call it the lattice energy. So this takes energy, right? And so when I say it takes energy, you have to put energy in. Okay, so you put energy in. That means that it's an endothermic process. Okay? When you make a bond, right? So put it this way, to put energy in to break a bond, right? Put energy in to break a bond. Right? And you can think about it really in terms of ions, it's really easy, right? It takes energy to pull two charged particles apart. And so you have to put that energy in. You have to use a force to pull them apart, right? The same idea for covalent bonds, only the difference is, well, in a covalent bond, you're pulling the two atoms apart where both of those two nuclei are pulling on that pair of electrons, right? And so it takes energy to do that. You have to put energy in. You do not get energy out when you break a bond. When you form a bond, right, it's the opposite, right? You bring two particles together, they lower in energy. They're attracted to each other if they're ions, right? And so they want to be closer together. And so as you form a bond, energy is released. It goes to a more stable state, okay? And we should inherently understand that when we form a bond that we release energy because, well, the fact that we exist is reason to believe that. Because when we form a bond, we go to a more stable state. If bond formation was less stable than not having bonds, the atoms that are composing our bodies would not be held together. Right? It would be less stable to have bonds, so the atoms would just be individual atoms in the cosmos, right? And so when we form bonds, we go to something more stable. Now, sometimes you may hear people talk about it in a not a very careful way. And one of the things that happens is in a lot of disciplines, we kind of learn it in a certain way, and we talk about things in shorthand. So you may have heard a biology professor say, when you break the ATP bond, you get energy out. And that's really a shorthand for, well, when you break the ATP bond, it takes energy to do that. But then after that ATP bond is broken, new things are actually formed that are going to be lower in energy than it was in the first place. And so when you hear a biologist say that, something now that you've had this training and this discussion in chemistry is, okay, you're breaking the ATP bond, but you're forming new things. When you form those new things, right, those new things are going to form new bonds, which are then lower in energy than the original bonds before. So now you can start to think about this from a chemistry standpoint in biology classes that you take, in that, well, it's not when we break the bond that it takes, or that we get energy out. It takes energy to break it, but we make new things that are lower in energy. And overall, we get energy out because the new things are more stable than the old things, right? The products are more stable than the reactants, okay? And so that's a key to bond energies and understanding the chemistry that's out there, is that it takes energy to break a bond, right? We call that the bond energy. And so you have to put that in. When you form new bonds, it's lower in energy, and so you get energy out, okay? It's a really key concept for understanding how things work in the chemical world. So that leads us now, we've looked at the two different types of bonding, ionic bonding and covalent bonding, and we are going to explore both of these a little bit more. Before we get there, we're going to introduce another of the periodic trends, okay? And this periodic trend, as you can see, is electronegativity, okay? So electronegativity, often, and it's not always used, but electronegativity is often abbreviated with this chi symbol. Sometimes you'll just see the abbreviation EN for electronegativity. The electronegativity is just a measure of how an atom attracts the electrons in a covalent bond. Now, when you look at the different elements that are out there, elements will attract those electrons differently because of things like their size and the number of protons in the nucleus. And when two atoms are bonded to each other, those atoms will share the electrons unevenly in many, many cases. If you think about a hydrogen atom, which is right here in the middle, well, a hydrogen atom will share electrons evenly because you have two hydrogen atoms that are pulling on the electrons that they're trying to share. So when they pull on the electrons, they each pull with the same amount of force, if you will, right? They still have, they have the same type of energy of attraction between the nucleus and the electrons that they're sharing. But if you have two different atoms, there's a good chance that those two different atoms are going to pull on the electrons with a different amount of force. And so if you can consider something like lithium hydride, in this example, the lithium is over here on the left-hand side, and the hydrogen, so your hydrogen's there, your lithium is over here. that lithium doesn't pull on the electrons as much as hydrogen does. And so the electrons spend more time over on the hydrogen, essentially, leading you to have this partial negative charge on the hydrogen and a partial positive on the lithium. And so this is something we talked about way back in chapter 4 when we looked at water as a solvent, is this uneven distribution of the charges. Well, this is where we're starting to have the explanation. It's a matter of this electronegativity. How much does one element pull on the electrons compared to another? And so it turns out hydrogen's electronegativity is somewhere middle of the road. If you actually look at fluorine, though, so our last of the 3 molecules that we're looking at in here, right, so our fluorine is going to be on the right there, and our hydrogen is over here. Fluorine is the most electronegative element. So this is going to really have this partial negative charge, right? And the other side, the hydrogen, will have this partial positive charge because now the fluorine is pulling those electrons much more strongly than the hydrogen is, okay? Now we're going to note the pull of, or the electronegativity in a difference in a bond by when you have 2 atoms that don't share the electrons evenly, you're going to put down what's called an electronegativity arrow to describe where the electrons spend their time. And that's really just an arrow. Okay, this arrow points toward the more electronegative element, right? So in this case, towards the fluorine. And on the other side, you put a little cross on it, okay? Now this is different from the arrows you might see in a physics class. It's not showing the dipole of the thing so much as it's showing the electronegativity difference and where those electrons reside. It's not showing the magnetic pole, I should say. Right, magnetic poles are described using arrows without the little cross on the back. And so when we do electronegativities, that little cross just tells us which side is the more positive side of that molecule or of that bond, okay? And so when it comes to the lithium hydride, right, you're gonna get a polarity arrow that's pointing toward the hydrogen instead because the hydrogen is more electronegative. Yes, Amir?
For something like the H2, it doesn't basically have any polarity either.
That's correct. Yeah. In something like H2, and we're going to talk about this other thing in the bonds that will be able to calculate whether there's going to be an electronegativity arrow or not.
Thank you.
Mm-hmm. All right, so here's some values. These values are for the electronegativities of the elements. So they're called the Pauling electronegativity values. This table is the same one you have on your equation sheet. Pauling is referring to Linus Pauling, the person who really came up with these initially. The Pauling electronegativity values are going to be values that allow us to, to determine the polarity of different bonds. And so the thing we're going to determine here, to determine whether it's polar or not, is what's known as the electronegativity difference. So we're going to call that delta En, okay? Delta En, okay, that's the electronegativity difference. Okay, and all that's going to be is essentially the electronegativity difference is going to equal the electronegativity of one atom minus the electronegativity of another atom in this bond. Okay. And it's going to, where at the electronegativity of atom A, oops, that should be En. Excuse me, I forgot my N's here. En. So where the electronegativity of the first atom is going to be greater than the electronegativity of the second atom. And so you're going to get a positive value each time. And the arrow, the electronegativity arrow, will show you which one is more electronegative. okay? And so the values that you have in this table, notice that there are no noble gases, right? Noble gases don't have electronegativities. They aren't trying to grab onto electrons so much in bonds. They tend to be monoatomic gases. They're not trying to form bonds here. And so we don't even have to think about them in this term. But what we can do is take values and see electronegativity differences, right? You just take one value minus another value. So in the example of HF that we had before, right? So you could say that delta En for HF would equal 3.98 minus 2.20. Okay, so you get a value of 1.78. And so if you were to draw HF, this would have an electronegativity arrow pointing in that direction, and it would have a magnitude of 1.78. So it would be pointing toward the fluorine, showing that the fluorine is going to be where those electrons tend to spend more time, giving it that partial negative charge, and the hydrogen the partial positive charge. And they're partials, again, because like we talked about with water when we were in chapter 4, they're partial charges because they're not fully ionizing, right? We're not talking about the fluorine totally taking the electron away from hydrogen, or the hydrogen totally giving up its electron. It's just that the fluorine tends to pull on to those electrons more, and those electrons spend more time on the fluorine. Okay. So this is going to lead us to another conversation, which is about bond polarity and what are called dipole moments. So the bond polarity, that comes about from these electronegativity differences. Okay, and that's for a bond. Okay, a dipole moment is the sum of the electronegativity differences. Delta ENs for all bonds in a molecule. And this is going to have to do with both the values that you get from the electronegativity table, those Pauling electronegativities, so you can calculate the electronegativity differences for all the bonds, but it's also going to have to do with direction, right? Because if the electrons spend more time on one atom versus another atom in a bond, well, if you have more than two atoms, then it can be somewhat more complex because you have to deal with where the electrons are, say among 3 or 4 or 5 or more atoms than that, depending upon the complexity of the molecule. But if you look at a diatomic molecule, something like HCl, right? This is diatomic. Means there's only one bond. Okay, in that case, the bond polarity will be the same as the dipole moment for the molecule. And notice that when we talk about a dipole moment, it's for a molecule. When we talk about bond polarity, it's for a bond. Okay. So if I think about HCl, I can calculate the electronegativity difference. And I can do that by going and looking at the electronegativities of, say, chlorine. So here's chlorine. Hydrogen we have already looked at, right? This 2.20. So I take the chlorine, which is 3.16 minus 2.20. Right, so I get a value of 0.96. Okay. Now these are unitless, so you don't need to worry about that, about units on these, but you get a value, a magnitude of 0.96, and the direction would be such that it would be, the electronegativity arrow would be pointing toward the chlorine with the cross on the hydrogen side, okay? And so that bond polarity is also the dipole moment, okay? And that's for something simple, only one bond there. But when you start to get multiple bonds, it now becomes important to understand the shapes of the molecules, which is something we'll get into more a little bit later also. Suffice to say, I'm going to give you some information about shapes of these 4 molecules, and we'll have more information later on how you can figure out the shape of the molecules once we get into what's called VSEPR theory later in this chapter. Yes, Amir.
I think I answered my own question, but just to be sure, when we draw the error, it's always toward the one with the higher electronegativity on the chart that you gave us, right? So
That's
we
correct.
calculated using the 2 numbers, and the error is always towards the one with a higher number.
That's correct. Yes.
Thank you.
So if we look at water, back in chapter 4, we looked at water as being oxygen bonded to hydrogens, and we drew it in this bent way. We'll see why that is when we get to VSEPR theory a little bit later. But it's going to be a bent molecule, and it has to do with where some electrons are on the oxygen. Okay. Now, if we take that and we say, okay, we can figure out the electronegativity difference between hydrogen and oxygen for each of these bonds. Well, oxygen, we'll go back up here. Oxygen's the second most electronegative element. Right? Fluorine is the most electronegative element. And so for that, we can say, well, 3.44 minus 2.20. So you get a value of 1.24. And in this case, the bond polarities, you're going to have 2 bond polarity arrows that are both pointing toward the oxygen. Okay. Now, the values of those arrows, I'm not going to worry about you guys calculating overall values. What I want you to know is if you have a value of 1.24, it's going to be a polar bond. And if you actually take those bonds and break them down into vectors, so this is something, again, we talked a little bit about back in chapter 4, is you can look at there being these arrows broken down into 2 components, a vertical component, and I'll put that in blue. So you have a small arrow there, right? Vertical as drawn on this page, by the way. So you have these little blue component of it, which is in one direction. And then we'll take a green arrow and show that, well, the other component of these larger electronegativity arrows can be drawn in that direction. But for the other bond, it's the equal in magnitude, but opposite in direction. So when you add up the green arrows, right? So you add up this green arrow plus this green arrow, right? You're going to wind up with 0, right? They're equal in magnitude, but opposite in direction. Whereas when you add the blue arrows together, right? Here, you've got these 2 blue arrows, which when you add them together, right, they're equal in magnitude and in the same direction. So you would get a blue arrow that's basically twice the length in that of the little blue arrows in that direction, right? Mind you, this is a lot of this stuff you can, if you had vector math before, this should be really, really straightforward. If you haven't, I highly recommend, that kind of a course that covers that. But basically what you can do with that is say, okay, based on those arrows, this particular molecule has a dipole moment, right, in this direction. So this would be the dipole moment, right, associated with this molecule, right? And that's really just the sum of these electronegativity difference arrows for each of the bonds. And so there's a directionality and a magnitude component to this. Okay. If you look at carbon dioxide, again, we're going to be able to draw these out a little bit better later on. But if you look at carbon dioxide, the carbon dioxide molecule is a little different. Now you can look at these this molecule in this way, but basically it's what's considered a linear molecule. All of those atoms are bonded in a row. Okay, so it's not bent like water is. They're all in a row. And you can do the electronegativity difference for this molecule in the similar way. So you can calculate the electronegativity difference of carbon and oxygen. So here we'll go back up to our table, and we know that our oxygen is here at 3.44. Now we have carbon, right? So 3.44 minus 2.55. Okay, so you get a value of 0.89. Okay, and so when you draw these in here, each of those are pointing toward the oxygen. So 0.89 from carbon to oxygen there, 0.89 from carbon to oxygen there. Now those two arrows, because of the molecule's linear shape, when you add those two arrows together, you find that those arrows sum to 0. And when they sum to 0, you get a nonpolar molecule. Okay, so it's a nonpolar molecule when you have carbon dioxide. It's nonpolar because the electronegativity arrows sum to 0. Okay, so you have two polar bonds in carbon dioxide, but overall, it's a nonpolar molecule. So that's carbon dioxide. Ammonia, and you're going to see these again when we start to look at shapes, but ammonia has what's called a trigonal pyramidal structure. And so this is where we're going to utilize something. We're going to spend more time on this later, but you'll start to see what's called a projection drawing. Okay. And so projection drawing, we draw in bonds using wedges and dashed lines. Okay. Oop, and I totally drew an oxygen. What am I doing? Here we go. These should be hydrogens. Okay. So when we do a projection drawing, okay, just as a note, we'll get better at this as we proceed in the class. If you have a line, right, that's a bond that lies in the plane of the page. So within the plane of the page. If you see a wedge, something like that, okay, what this tells you, and we're going to say A and B, okay, and with this particular version, right, this is a wedge. It says that atom A, sorry, actually we'll do this a different way. Yeah, so atom A is in the plane of the page. And atom B projects out toward you. Right, or is closer to you. Okay. And then the other version of drawing bonds in projection drawing is when you have atom A, and we'll call it atom C. Okay. This is a dashed line. Okay. Atom A is in the plane of the page. And atom B, or atom C, excuse me, projects away from you. Okay. So it's farther away. And it's somewhat hard to see, but your textbook has some images that will show you some of these projection drawings and sort of some space filling models that will make it easier to see. But essentially, this is what allows you to represent in 2 dimensions a 3-dimensional object. Okay, we're drawing it using this perspective. Just like if you were to take a drawing class and draw, say, like a cube, right? The farther back part of the cube, if you're drawing it on a piece of paper, right? A piece of paper is 2-dimensional, but you would draw the back end of the cube as being smaller than the front of it. Right? That same idea holds here, and that's why with the wedge, the bigger part of the wedge is the part that's coming out toward you, right? And the smaller part of the dashed line is the one that's going away from you. Okay, it's meant to show that. Now, if we look at the electronegativity difference between hydrogen and nitrogen, again, we go back here and we can look, here's our nitrogen, 3.04, and hydrogen. Change colors here for a second. So we can look at our electronegativity difference. It is 3.04 minus 2.20. So that's going to equal 0.84. And they're pointing toward the nitrogen. And so each of these bonds has this polarity arrow. And if you sum all 3 of those polarity arrows up, they're going to be in a direction that's basically pointing from the nitrogens on up. So if you can see in this type of a picture, right, you've got sort of 3 hydrogens coming down from a nitrogen. So there's a hydrogen coming off of the nitrogen at each of the 3 points, sort of like a tripod, right? And so overall, the electronegativity of the molecule is going to be, if you were to draw a line from the middle of the nitrogen down in a way that is right in the middle of those 3 hydrogens, right? That would give you an idea of the directionality of that bond polarity. So it'd be pointing up toward the nitrogen from below, if you will, if your hydrogens are the bottom parts of a tripod. Okay, and so the ammonia molecule is polar, with this green arrow here representing the dipole moment for that molecule. Of course, if you were really doing it right, the dipole moment for this molecule would be right through the middle of that molecule. Right? So it would be something like in there, right? I just write them off to the side because it's a lot easier to see the molecule when your polarity arrow is written off to the side. Okay. Finally, the last example that we'll look at as far as molecules to be drawn to represent polar versus nonpolar molecules, we'll look at methane. So methane is a tetrahedral molecule. Again, more on that when we get into VSEPR theory. Okay, so it looks something like that. The electronegativity difference here. So on this one, we can actually look at the electronegativity difference, the delta En of, well, carbon, we've actually done carbon, is 2.55. And hydrogen is 2.20, okay? We're gonna find that there's a spectrum here. So if you actually look and do that calculation, you get a value of 0.35. We're actually gonna consider that to be nonpolar, okay? And so we'll see that spectrum and why it's nonpolar later on, but basically it means that they're sharing electrons close enough, and so there's an arbitrary cutoff, if you will, about that. But what you can kind of think about with this is, well, it would be directionally very tiny arrows. Each of those tiny arrows pointing toward the carbon, okay? And those tiny arrows are so small as to be insignificant, and on top of that, they're all pointing in toward the middle here, and they're pointing it in toward the middle from sort of evenly spaced directions, thus they all cancel each other out. So similar to carbon dioxide, any type of polarity that could be part of this molecule would be canceled out by the directionality of those little tiny arrows, okay? And so this is going to be a non-polar molecule as well. And so this is a harder one to see because of the nature of this tetrahedral orientation of the molecule, or of the atoms that are surrounding the hydrogen atoms surrounding the carbon. But hopefully, as you start to see more molecules as we proceed through this chapter and through chapter 9, and as we do Lewis structures a little bit later on, you'll start to be able to get a feel for what a tetrahedral molecule looks like. Now, in the ideal situation, we would be in class, and it's easier to demonstrate that in a lot of respects in person when I can bring in some models, and you can see those models really easily, okay? And so it's really incumbent upon you to take some time, spend some time with your artist rendering in your textbook to see what these molecules look like. That will help you a whole lot in visualizing the shapes of molecules, which is important for basically the rest of chemistry here on out. Shapes of molecules have a lot to do with things like reactivities, with how different atoms interact with each other, with physical properties to some degree as well. So that's something that it's important that you spend some time and really start to be able to visualize these molecules three-dimensionally in your head, even though we can only depict them in 2 dimensions on a piece of paper. Okay. So I think this will be the last thing we get to today, is ions and electron configurations. Okay, so when we've done electron configurations, and we did a bunch of it last week, we've always done it for atoms. Here, we're going to look at the electron configurations of ions. And we're going to do so with sort of a framing of this first, and that's the following. If we think about in covalent bonding, okay? So in a covalent bond, when that covalent bond forms, it's going to form between, as we know, right, 2 nonmetals, okay? So that's something we've talked about in the past. 2 nonmetals, they're going to react, they form a covalent bond. When they do that, they share the electrons, okay? Something we have just gotten to now is that when they share those electrons, the way they're doing it is such that they fill their electron configuration of that valence shell, okay? And they fill it so that they get to a noble gas electron configuration, because there's this inherent stability to a noble gas electron configuration, and they want to get there, okay? So nonmetals do it by sharing electrons with other nonmetals and forming covalent bonds, okay? And so that's a key here, right? Getting to this noble gas electron configuration is going to be an important part of atoms forming bonds. If you have an ionic bond, however, we know that an ionic bond, just as a reminder of things we've talked about in the past, right? It's a metal and a non-metal, right? Okay. When you have a metal and a non-metal, the metal has a very small electronegativity, and the non-metal has a very large electronegativity. And so they're going to form these ionic compounds where, and this is an important thing to understand, is when they do that, the valence orbitals of the metal are emptied. So any electrons that were in the valence orbitals of the metal are gone, okay? And the valence orbitals of the non-metal are going to be filled, okay? Now, this basically is something that happens because those nonmetals really want the electrons very, very much, right? Remember, those nonmetals have very high electron affinities, okay? And so they become more stable when they grab onto these electrons, right? The metals, however, have ionization energies that are very small. And so they're happy giving up those electrons to the nonmetals. Now, when the nonmetal takes on these electrons, it gets to that noble gas electron configuration, okay? And that's a key here, again, is when the nonmetal makes an ionic bond, it's going to fill its valence orbitals and get to the noble gas electron configuration of the next noble gas on the periodic table. So the one that's basically at the right-hand side of its period. Whereas the metal is going to empty out its valence orbitals, and so it's going to go back down to an electron configuration that's the same as its core, right? The core electrons of that metal. So essentially, it's going to have the same electron configuration as the noble gas in the row above it when it gets rid of its valence electrons. Yes, Amir?
If we happen to have time, can you give us an example on that ionic bonding explanation? It's a little bit hard for me to visualize it, saying for something simple like sodium chloride.
Sure. That's easy to do. So if you think sodium fluoride, right? So sodium, and hold on, do I have that? Yeah, so come on, computer. There we go. So sodium fluoride, it's a good one, okay? Based on what we know about this, right? If you were to have aqueous sodium fluoride, right, we know that it's going to make sodium ion, Na+, plus fluoride. Right, so understanding the sodium electron configuration, okay, so this is sodium metal, okay, versus sodium ion. Okay, so sodium metal is going to be, okay, so here we've got neon 3s1, right? Or if you want the full one, right, it's going to be 1s2, 2s2, 2p6, 3s1, okay? The electron that's lost, right, is that 3s electron, right? So the sodium ion is going to have the same electron configuration as neon. Or if you want the full electron configuration, 1s2, 2s2, 2p6. That's your cation, okay? If you, and so it's getting that, and so that's kind of the key here, right? It's getting that noble gas electron configuration. If you look at fluorine, right, fluorine is going to be helium, okay, 2s2, 2p5, or if you want the full electron configuration, 1s2, 2s2, 2p5. So, but it's going to gain an electron, right? It's going to gain an electron, and so where's that electron going to go? It's going to go into that 2p orbital, okay? And so when fluorine becomes fluoride, it becomes now helium 2s2, 2p6, or 1s2, 2s2, 2p6, okay? Which, by the way, is the same electron configuration as neon, right? Now, the proper way of writing the abbreviated electron configuration would be that, right? So it's filled its valence orbitals being the 2s, 2p orbitals, right? Whereas sodium vacates its orbitals, right? Gets rid of its 3s orbital electrons to go down to the neon electron configuration. Okay.
Thank you very much.
Mm-hmm. Now, the other part of this is isoelectronic ions and size. And so one of the things we're going to start to explore tomorrow, and we'll pick up with this this stuff, right? We now understand, or should have an understanding of, what happens to the electron configurations of ions when they are formed, when ions are formed from their elements. And tomorrow we're going to take and start to understand how electron configurations of ions, and the fact that a cation has fewer electrons and an anion has more electrons, and we're going to relate that to the size of the ions, and we're going to introduce this new thing, which is isoelectronic ions. where isoelectronic just says they're going to have the same electron configuration. And one example of which is from our previous slide, where the sodium ion, Na+, and the fluoride ion, F-, actually have the same electron configuration as neon. They have the same electron configuration. They're going to be considered isoelectronic. And so we'll dive more into that tomorrow. All right, guys. And so that will do it for us for today.